All right. Oh. I don't know why it does that. Cool. All right, y'all. Well, I'd say welcome back. I don't know if it's welcome back for me. Good to see you all again. Glad to be here. Again, sorry I couldn't be here last Thursday. So, yeah, I was out with the Busch Gardens field trip. Largely went well. The day was beautiful. The wait times, like 10 minutes, 15 minutes to get on the roller coaster. So that was awesome. At the end, it got messy because a couple students were 30 minutes late to the bus, and that was stressful. Didn't exactly know where they were. So, otherwise, yeah, and then when the bus ride home, one of the buses was leaking coolant. Another bus had to pick us up on the way. So the end was a little stressful. I got home, if it makes you all feel better, I did not get home earlier. I got home at 8:30. Yeah, it was a long day. It was good. But the next day, it was nice being back in the classroom and not being responsible for 250 students 100 miles away from. Anyway, but I'm back. So, I mentioned this in class, but yeah, the free response, I should have those in tomorrow or Thursday. I got those all graded. Averages are looking good on those, so there probably won't be a curve or anything on those. The average on one question, so the one that was the voltage resistance, that one less people chose. That one had an average of a 75, which isn't bad. That's still like decent. The one with the vectors, electric fields, that one averaged in the 80. Which overall, I'm pretty happy with. So those will go in tomorrow, Thursday, and then everything will be kind of up to test 1. Everything will be up to date. Everything up to test 1, and that's a good benchmark of kind of how you are doing. So today we are going to move into magnetic forces and fields. That's going to be the next 3 weeks, is magnetic fields. Okay, we talked about electric fields. This is the other side. The electromagnetic force, electric force, magnetic force. These are two sides of the same coin, which is really weird, and you don't need to know. It turns out electric fields, depending on how you look at them, can end up being magnetic fields. And magnetic fields, depending on how you look at them, can be electric fields. You don't need to know any of that. That's not something but I just mentioned that these are kind of one and the same, electric fields and magnetic fields, even though they won't seem like they are at all, but they are. So we're going to spend time on that, but I want to do a recap of last week. So last week we talked about DC circuits, direct current circuits. So we had resistors in series and parallel, and we had capacitors in series and parallel. And that was basically the whole week is resistors in series and parallel, calculating current, calculating voltage, calculating resistance. Capacitors in series and parallel, calculating charge, calculating voltage, calculating capacitance. That is what the entire problem set is doing. If you all just look at this, every problem is find the net resistance, find the current, find the voltage, find the charge, find the current, find the... it's just doing the same thing in a bunch of different ways. So let me kind of give you all the rundown of what you need to know to be successful and how to approach these. We'll spend just a little bit of time on that before we jump into magnetic fields, because I want to make certain you are good with this. These problems, they just take practice. There's no getting around it. You kind of have to work through them, but I'll tell you what you need to know to be successful. How do you solve these problems? So when it comes to capacitors, there's like some concepts you need to know, and then there's the problem-solving strategies for these problems. So, and these are everything I'm going to put here. This is in the magnetic fields thing, so it's at the beginning of this. So for resistors, you need to know how to add them in series. You need to know what series is, one after the other. They're all along. There's no junctions between them. They add up, well, we'll get to how you combine them, but when they're in series, so what is series? They're all lined up. Current is constant. Current is constant in series. You have to know, you can put that on your note card, but that will not be given on the formula sheet. That's one of those things you will need to know, that in series, current is constant, and we're going to talk about why. Well, there's a reason why you need to know that, but for now, just trust me. In parallel, you know what parallel means? It means that they share kind of this wire on this side. There could be junctions, that's fine. But on one side, they all kind of share that wire. There's no resistors between them. On the other side, they all share kind of the same wire. And in parallel, voltage is constant. Remember, voltage is like height. So one end is high, one end is low. If we looked at this picture down here, for example, like the current on this, or the voltage on this side, let's just make up a number. Let's say it's 12 volts on this side. On the other side, let's make that orange. On the other side, it's all the same voltage. And let's just call that 0. So every single one of these has a voltage of 12. 12 to 0, 12 to 0, 12 to 0. Voltage is kind of like this height. Current is like a flow. It is defined as a flow of charge. Current is how the charge flows. Doesn't matter as long if there's one path. That's why the current's constant here. Current is not constant in parallel because of these junctions. Every time the wire splits, it's like a river that's splitting. And current is that flow of water, of charge. And every time there's a junction, it's splitting. Okay? So, current is constant in series, voltage is constant in parallel. Capacitors, one of these rules is the same, the other one looks very similar. For capacitors in series just one after the other, same thing. Charge is constant. So the charge is capital Q. The charge that this one has is the same as the charge the second one has. It's the exact same. The logic for, well, I'm not going to spend too much time on the logic for why that is, just because it'll probably end up being more confusing. I just want to point out the main ideas here. Charge is constant. They both have the same charge. In parallel, we get to use the same rules before. In parallel, voltage is constant. It doesn't matter what's in parallel. Stuff's in parallel, voltage is constant. For this exact same logic that I said before. If this side is 12 volts and this side is 0 volts, the junction doesn't change that. This capacitor has a voltage of 12 volts. This one has a voltage of 12 volts as well. For the exact same logic as resistors. Okay? So you need to know this. And I'm gonna tell you why. We're gonna look at some problems. We'll spend some time. Why do you need to know this? We'll get to that. Okay, so when they're in series and parallel, to solve these problems, so kind of here's what happens if you have resistors in series. How do you solve circuit problems? Let's just put it that way. How do you solve DC circuit problems? The first step, combine all your resistors / capacitors. I will not give you a circuit with resistors and capacitors. It will be one or the other. All resistors or all capacitors. We're not going to bother with RC circuits in this class, really. There will be a question of discussion, but I will not test you on RC circuits. RC circuits literally means resistor, capacitor, as in they're in circuit. So, whatever. Combine all your resistors and capacitors into one resistor / capacitor, i.e. R net or C net. Net meaning total. So take all your resistors. If they're in series, add them together. If they're in parallel, add them together. You can only, well, we'll do an example of this to show you how you actually do this. Combine them all into one resistor capacitor. Why? This net resistor / capacitor will have the voltage of the battery. Okay? And you may be like, so what? Why do I care? Why does it matter if I have... Let's just draw a picture of a really simple example of this. So if I have, and this is actually one of the problems, this is like the simplest problem I can give you on this. Let's just say that this one is 5 ohms, and let's say this one's 10 ohms. And let's say that this voltage is, I'm going to pick something really easy. I'm going to say 30 volts. A very common problem I can ask you, and this is basically what the whole problem set is, what's the current through the first resistor? That's a really common problem. What's the current through the first resistor? As it stands, we can't figure that out. We can't figure that out based on what we see right now. But what we can do, this is in series, So if I combine these together into one resistor, so this is in series, so the net resistance will end up being 5 plus 10, which is 15 ohms. Why is that helpful? Why did we combine into one resistor? The voltage of that resistor is the voltage of the battery. When you have one resistor, the voltage of this resistor is the voltage of the battery. And if you know voltage and you know resistance, V equals IR. We can find the current. We can find the current, and I was purposeful here. So V equals IR. We rearrange this. I equals V over R. I purposely picked nice numbers, so 30 over 15 equals 2 amps. So that's my current. That is the current in that. Now, this hypothetical problem, I didn't say find the current in the net resistor. I said, what is the current in the 5 ohm resistor? This is where I told you all, you need to remember in series, current is constant, and parallel, voltage is constant. Now we actually get to use these rules. This is why you need to know these rules. You go backwards. So the step 2 here, I'm going to give myself a bunch of space for this. Find the current / charge on the net resistor / capacitor. Work backwards to find the current, charge, voltage on each resistor. And I'm going to make this look way nicer by stretching this. Okay, this is the process. So if we work, great. We did it. We did step 1. We did step 2. We found the current charge on the net resistor capacitor. You go backwards. You say, what did I originally have? Was it in series or was it in parallel? It was in series. Because it was in series, this one has 2 amps. This one has 2 amps. Current is constant in series. I have current. I have resistance. You can actually find voltage. 20 volts here, 10 volts here. That's how you solve these problems. Every single problem follows this process. Find the net resistor / capacitor. Find all the things for that net resistor and then go backwards. And this is the simplest type of problem I can give you. I only had to combine it once. So I keep saying this is the simplest. What does it look like when things are worse? So first, let me just remind you all, how do you add? So again, this slide, all this stuff, I will upload. Let me actually save it as today's date. So this will be on here, so you all can kind of review this. The reason I'm spending the time on this is because I wasn't here last Thursday to clarify some of these things. I really want to make certain you all know the main ideas from last week. So this is how you add them. I said you have to combine them. Here's how. Here's the math. You just kind of have to practice doing that math. Resistors in series, really easy. Just add them up. Resistors in parallel, you have to do all this. I'm also going to show you all, just real quick, R net. You can look at the algebra for yourself. Ends up being this. 1 over R1 plus R2 plus ... 1 over Rn. So, kind of check this out later on, see what the heck I did there. But just know that when you're solving R net, it's not just 1 over R1 plus 1 over R2 plus 1 over R3. Put that in your calculator and it's done. You have to do 1 over all of that. You can look at the algebra yourself, why that is. But I want to mention that. Capacitors is the exact opposite rules. In parallel, they just add. In series, you do the 1 over plus 1 over plus 1 over. Great. Okay, so that's just math. Honestly, this is the easiest part of what I'm telling you all. It's just the math part. What's the hard part? When you have a circuit like this. So, I told you all the first step is we need to get the net resistance. I currently have 1, 2, 3, 4, 5, 6 resistors in this circuit, and I need to take this and make it into 1 resistor. This is the worst case scenario. This is the most complex kind of problem I'd give you. And to begin this, the question is, which resistors can I combine first? I say should, it's really can I. And how do you answer that? Which resistors are in only series or which resistors are only in parallel? If they're both in, like, you'll see what I mean when we answer this. So just for now, which ones can we combine? Which resistors? Are there resistors that are in parallel with each other? Are there resistors that are in series with each other? Which ones are we allowed to combine? Can I combine R1 and R4? So R1 is right here. I'll make this picture a little bit bigger to make it easier to see. R1 and R4, I'll just kind of, well, I normally hide it. There's R1, there's R4. Are those just in series or are those just in parallel? If you're like, no, then you can't combine them. R2 and R3, are those either in series or in parallel? If your answer is no to both of those, can't combine them. R5 and RA, are those in series or are they in parallel? If so, you can combine them. If not, can't combine them. R1, R2, R3, are those in series or parallel? That's the mindset. So take a guess. Take a guess on this. I'll straight up tell you, you have a 50-50 shot of getting this right. But you're like, there's 4 options. What does that mean? I'll let you think through it. You got a 50-50 shot of getting this answer right. If you're just like, I have no idea. Guess. 50-50 shot. And again, it all boils down to which ones are in series exclusively or which ones are in parallel exclusively. All right, we'll go to 205. Again, this is basically just guess. Like, if you're not sure, just guess. There's no math here. So we'll close it out in 5, 4, 3, 2, 1. Okay. So let's just go one by one and see. So R1 and R4. Are those in series? That's kind of our first check. I have a junction. Oops. R1 and R4, are they in series? I have a junction between them. So no, they're not in series. Are they in parallel? I check if I can go from this end to the other end. Do they share that wire? Oh, there's a battery in the way. No. That's how you check if they're in series and parallel. Do they share the same wire on both sides? No. This one runs into some resistors. This one runs into a battery. Parallel means that they should be sharing the same wire. On this side, sure, they're sharing that wire, but on this side, I run into some crap. If I kind of color the other side, this one, no matter which I run into some crap. I run into nope, they don't share the same wire. There's crap in the way. So that's how you determine parallel. All right, so no, not that one. Next one, R2 and R3. So R2, R3, are they in series? Yep. There's no junctions between them. I can go from one to the other, no junctions between them. So that is one of my correct answers. That one's in series. I can combine those. I'm allowed. Nothing's stopping me. R5 and RA. Are those in series? No. There's a junction on the side, so not in series. Are they in parallel? I draw this line. Can I get to the other resistor without running into another resistor? Yep. So that side they have in common. This side, yep, they share the same wire on that side, so they're in parallel. So these ones are in parallel. That's kosher. All right. R1, R2, R3. Let's look at that one. R1, R2, R3. Are they in series? Nope, there's a junction in the way. It splits. Not in series. Are they in parallel? They share this side. Well, 2 of them do, but this one, no. They're not in parallel. These 2, yeah, we already said these 2 are in series, so no. That one, not in parallel. All right, so that's why you had a 50-50 shot. Okay, I'm going to kind of I am not going to do the math because I don't have the time for it. But like the math is the easy part. So what I'm going to do is I'm going to take this picture and I'm going to show you how we can take this and we can go from 6 resistors to 1 resistor. So kind of just what we showed there. We found the first ones together. So we have this circuit. This problem just has a bunch of steps. Not hard steps, but like let's just get through it. All right. So we have our original circuit. We said which ones can we combine? Well, let's just combine these ones first. These ones are in series. So what I'm going to do, as fun as this may sound, it is kind of just the safest bet. I'm going to redraw the entire circuit. So what I did here, and I'll go ahead and I'll color code these things. So if they're in series, we'll do red. So these are in series. So I combined them. What do I call that resistor? I call that R2, 3. Just kind of I combine 2 and 3, call it R2, 3. Makes sense. And then I got the rest of them. I've got R1, I've got R4, I've got R5, I've got R6. Next, we keep combining. What's the next one we combined? Well, we kind of already identified this. So we'll do this one in purple. We can combine 5 and 6. Those are in parallel. So these are in parallel, so I'm allowed to combine these. Now, when you combine them, you got to do the math. How do you combine series resistors in parallel? 1 over blah, 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 that thing. So we draw another circuit. Again, this is the worst case scenario, y'all. I am showing you the worst possible problem we can have on this. So we combine these into 1 resistor. What do we call it? R5, 6. We took those 2 resistors and we combined it into 1. We still got R2, 3 here. And we still have, this is RA, not R6. So we'll call it R5A, whatever. It's still the same idea. Okay. I want you all to look at this and see if you can identify the next ones we're going to combine. Which ones are purely in series or purely in parallel? There is only one option that's correct here. The option that's correct is R4 and R5A are in series. Who cares about that corner? There's no junction between them. So these are in series. So the next step is we combine these guys. So we have our R1. We now have, let me give myself a little bit more room. R2, 3 is right here. That's still existing. And now we have, what are we going to call this one? I'm kind of running out of room. R4, 5, A. Because I combined 4 and I combined 5A. Like it's the best notation I've kind of thought of for this, but you do whatever notation works for you. All right. Next question to y'all. Which 2 do I combine now? We say, are there any exclusively in series or parallel? Yeah, those are in parallel. So we're going to combine these ones with our nice purple color. Boom, we still got R1. And now we have R2, 3, 4, 5A. You could call it 4, 5A, 2, 3, whatever. Just we put all the letters together. Okay? And the last one. So these were in parallel. The last one is hopefully fairly obvious. It's the only ones left. We can finally combine this into 1 resistor, R1, 2, 3, 4, 5A. That's our net. Okay. A lot of steps. Why did we do this? Remember, by getting to one resistor, in this problem, the voltage of the battery was 5 volts, which means that the voltage of this resistor is 5 volts. I can then find the current. Current equals the 5 divided by R net. R net is that thing that we just found. Why is that useful? Now we go backwards. So let's just go backwards. Current is constant. Why? Because it was in... Actually, let's put this in the color that we used. These were in series. In series, when we go backwards, current is constant. So the current that you just found is the current in R1 and the current in the other one. Now you can find voltage in those two. And then you can find, now you know voltage, current, and resistance for those two resistors. Great. Why is that useful? I can go backwards to the next step. The last step before that, they were in parallel. I know this is getting a bit messy because there's just a lot of detail on here. When I go backwards, parallel, voltage is constant. So the voltage that you find in those carries to the step before it. Oh, great. Now I know the voltage of this and the voltage of this. I can find the current in those. And you just keep going backwards and backwards and backwards, filling in the thing. There is no shortcuts to this. This is the process you have to do for this. You have to condense it to one resistor, find the voltage, current, resistance. Go back a step. Whatever's constant, you get to keep. Then do the voltage, current, resistance for all the resistors. All right, go back another step. Whatever's constant, you get to keep. Voltage, current, resistance for all the... This is the process, y'all. There is some video. So in my video thing I posted, like the stream I sent you, I solved through one of these. There's tons of videos of people solving through these. Tons of examples. But I at least wanted to tell you all what the process was. In person / whatever. And now you just kind of got to hash through these. Once you do a few of these, you'll be good to go. But at first, it won't make sense. But it is just, there is a process to these problems. What is that process? It's the thing I wrote down for you all right here. Combine them all. Find all 3 things. Then go backwards. However many times you need to. Yep. All right. If I had my way and had all the time in the world, we would actually do one together because this is like, there's a lot of steps here. There's a lot of decisions. But nature of college. Try these out, y'all. Send me emails if you're confused. Okay. Do you all have any quick or any questions about this? Okay. This was a lot. Okay. Please, if you're confused with this, at any point, shoot me emails. But again, I just showed you all the worst case scenario. That's as bad as it gets. That's as gross as it gets. Would I give one this complex on a test? No. This takes too long. Would I give one that's maybe a little bit less complex? If you all look at your problem sets, would I give one that's like this many resistors? Maybe this many? Yeah, 3 or 4 resistors, that's fine. So that's, if you can do these problems, 8, 9, 10 on the problem set, you're good. All right? This is kind of the level of difficulty that I would ask. I would not ask one like what I just gave you, but I wanted to show you that just because it had a lot of steps in it. Like it did, we got to make the decision a bunch of times. Series of parallel, series of parallel, series of parallel.
Would a question like that potentially be like a free response question?
It would be a great free response because it's got a lot. Yeah, I would not ask this as a multiple choice. If a problem takes you up to 10 minutes to solve, that's free response. Yeah. If one step, now, might I ask you one step of that? Maybe. Like, for example, this problem here, maybe I would ask you on a multiple choice, hey, what's RA for? That would be a reasonable multiple choice question, because that's, they're in parallel, takes you just a minute or two. If you know what you're doing, the multiple choice questions should not take you more than 2 to 3 minutes. If you know what you're doing. I give you all kind of 60 minutes for 20 multiple choice. That's like a 3-minute max. Hopefully some of the questions you know what to do take you 30 seconds. Some of them you maybe have to figure out take you 5 minutes. It averages out. That's the logic in my test design. The free response, I'm expecting I give you all like 20 minutes for. It's kind of how the time allocation works. With the expectation, if you know what you're doing, 5 to 10 minutes. That extra 10 minutes, the buffer, in case you have to figure it out. Yeah, it's a great question. Yep. All right, so getting into today's stuff. So that's DC circuits. Like, we're done with circuits. Now the next 3 weeks is all magnetism. Everything we're going to be doing moving forward is now, we will swing back to circuits at some point, but that's kind of on the last thing. So what do you need to know? Vectors. They're coming back. To be honest, they're coming back, but it's not going to be as bad. You're actually not going to have to do too much component stuff with this. Okay? Cross products, like I say cross products, but with a big old, like, not really. But it's going to come in. Current is defined as the direction positive charge is moving, just that concept, and centripetal force. You may be like, what? That seems the most out of place. You'll see. We're going to have things going in circles. If you don't remember any of these things, they will get reminded to you as we're going through this. All right, this is a lot. But basically, we're going to learn what magnetic fields are. We're going to relate how we're going to learn how you make them. We're going to learn that they come from current and they're related to current. We're going to learn that they affect wires. Magnetic fields causes forces on wires. And a lot of this is going to be right-hand rule. You'll see what I mean. It's going to be, how to put it. During the test, everyone's going to be looking silly. You'll see what I mean. All right. Why do we care about magnetic fields? Growing up, even maybe now, you probably play, your fridge has magnets on it. Woo! What's wild? I am not going to teach you anything about permanent magnets. So ironically, the things that you expect to learn about, you're like, oh, magnets, the things I play with. I am not going to teach you anything, I'm going to teach you very little. They have a north pole and a south pole. Magnetic field lines point away from the North Pole and towards the South Pole. The magnetic fields are strongest at the poles. Great. That's everything you need to know about permanent magnets. And that's going to come in later. That's it. That 3 sentences I just gave you. Everything else is going to have to do with current carrying wires. Okay, so to that end, why do I care then? These things are this is how we make electricity. Magnetic fields are necessary for making electricity. You're like, you may not have any clue. Trust me, we'll get there. So generators, light, a magnetic field, so electromagnetic waves is another name for light. Half of that word is electro for electric fields. The other half of that word is magnetic for magnetic fields. So light is just electric fields and magnetic fields, which, that may be weird to you. We'll talk about light at some point, but yeah, light is an electric field and a magnetic field. The electric field goes up, down. The magnetic field goes left, right. And, that's what light is. MRI machines, magnetic resonance imaging, use super strong magnetic fields to detect the resonance of water molecules, I believe, in brains, and that's a whole thing. We're not going to learn too much about how those work, but just know they require magnets. Super important. A compass, being able to tell which way north and south is, that's fairly useful. Mass spectrometry. You may be like, why is that useful? If you have some particle and you want to determine what that particle is, this is one way of doing it. So like forensics and stuff like this. This is a way to determine the composition of some material. You shoot it through, you ionize it, you shoot it through a magnetic field, and based on the arc that it takes, based on the path it takes, you can determine the mass of that molecule. So how do you measure the mass of molecules? You use magnetic fields. We'll talk about that. Again, fridge magnets, really not that much. Passive satellite orientation. That sounds really fancy. one way, like a question comes, how do you make certain a satellite keeps going the same path? If you put a magnet on it, it lines up with the magnetic field of the Earth and it'll just stay on that path. Whatever. Again, hard drives, funny enough, these are going out the window. It used to be back in the, like I say, back in the day. You may or may not have a hard drive. Everyone mostly has SSDs, solid state drives nowadays. Hard drives were the old school. This is still the cheapest way, but they're really slow. It's literally a disk that spins really quickly. And the way you store information on that disk is by, you magnetize it. If it's magnetized up, that's a 1. If it's magnetized down, it's a 0. It's how your all's credit cards also work. So that black strip on your credit card is actually a magnet. At some points it's magnetized a certain way. At some points it's magnetized another way. When you swipe it, the card reader literally just measures the magnetic field and determines 1s and 0s. You all don't need to know that, but I just want to show you so much application of magnetic fields. It's literally all around you. Honestly, the most important one is this is how we make electricity. Generators. Also connected to that, the opposite of a generator is an electric motor. So a generator uses magnetic fields to make electricity. We can do the opposite. We can use electricity to make motion. So electric skateboard, literally any electric motor, magnetism is involved. So super, super, super important. Obviously, you can exist without knowing this stuff. But I just want you to know, why do we care about magnetic fields? They are absolutely critical to our society existing, our power generation, all of that. Whatever. All right, so first definition, what the heck is magnetic field? The definition here is going to sound weird, but I'll hopefully explain it. A field which is responsible for the force a moving charge experiences. So first I'm just going to kind of read through this and I'll unpack it. A magnetic field, what is it? It turns out if you have a moving charge, shoot a proton across the room, shoot an electron across the room. If there's a magnetic field, that charge will bend. That charge will bend its path. Why? We make up this thing called magnetic field to explain it. The unit for it is Tesla. That's what the car company got its name from, which also got its name from the person who came up with it. It is also measured in Gauss. I will straight up tell you all that anytime I ask you for magnetic field, we're just going to use Tesla. Tesla will be our unit. 1 Tesla is really strong. So like an MRI is about 10 Tesla. Really strong. An MRI, again, you all probably know this, but an MRI is so strong that if you have any metal in your body, it will literally rip it out of you. Assuming it's a magnetic material, the 3 elements that are magnetic are iron, cobalt, and nickel. Aluminum is not magnetic. Copper is not magnetic. Specifically paramagnetic. Meaning if you bring a magnet near a piece of aluminum, nothing happens. If you bring a magnet near a piece of copper, nothing happens. If you have a piece of copper and you put it in an MRI, it's fine. Though it could get hot. That's a whole different thing. 1 Tesla is super strong. The variable for this is B. And it has the least satisfying explanation. I think this is the explanation. It's been a little while. Why is magnetic field B? Wouldn't it be great if it was M? I agree, yes. The guy that came up with this literally was listing vectors. And he just had vector. He had, this one is A. This one is B. This one is C. This one is D. Magnetic field was B. He was just listing them A, B, C, D. And this one got B, and that's how it was the first person to define it, so it gets B. All right. Okay. We no longer just have up, down, left, right. We have to actually work in 3 dimensions, and I am not going to try to draw things 3-dimensionally for you all, because that's just so hard. How do you draw something out of the page? How do you draw an arrow that points out of the page? This. A dot points out of the page, and X points into the page. That is the notation we use. It's actually very easy to remember with this, sound like almost like a clickbait video, with this one simple trick. You too, but it totally works. If you imagine this like a bow, like an arrow that you shoot from a bow, if you saw that arrow coming at you, you'd see the tip of the arrow, which is a dot. If you saw that arrow going away from you, aka it was getting shot into the page, you see the feathers on the back. It sounds really silly, but that's what helps me remember it. X is into the page, like if you saw the back of an arrow, it was pointed into the page. If you saw the arrow coming at you, you'd see the tip of it, which is a dot. It's kind of handy. My memory sucks, so any trick like this is great. And yeah, I mentioned this one Tesla. Okay, so back to this original definition. The field that's responsible for a force. This is how every field is defined. How is a gravitational field defined? A gravitational field is defined as, hey, I have something with mass, and it falls. It experiences a force. Why? Let's just make up something called a gravitational field. That's what's causing it. When we look at electric field, what's an electric field? Hey, I have two charges and they repel each other. What? They're experiencing a force. Why? Because there's an electric field. Fields are our reason for explaining forces. If there is a force, there is a field causing it. The question is, which field? If you have a mass, gravitational field. If you have a charge, electric field. If you have a moving charge and it experiences a force, magnetic field. Okay? So basically, how did this get discovered? They shot an electron through, they have permanent magnets exist. Like when lightning strikes certain metals, you get something called a lodestone. So way back in the day, people discovered that there was these chunks of metal that when you brought them near other pieces of metal, they got attracted to it. Those were permanent magnets that they just found out in nature. They're called lodestones. And so, they knew these things existed, and at some point, someone shot some charges past it and noticed that it did weird things. That it did not behave in a way that the magnetic field, that the electric field could explain, or that the gravitational field could explain. And if something is happening and our current knowledge doesn't explain it, there must be something new, or our current understanding needs to change. So, this field was introduced because, hey, charge is bent when they pass through this thing. What's causing it? Must be a new field. Magnetic field. Okay? You don't need to know all that. What you need to know from this is the unit, the variable, and this part, but it's kind of nice to know where these things are. Okay. So this is how it was discovered. A moving charge experiences a force due to an external magnetic field. A moving charge. That charge has to be moving. If the charge is not moving, the magnetic field does nothing. Why? Because that's how the world works. That's literally this is one of those, this is an observation of reality. Why does this happen? This is one of those fundamental observations. The world works a certain way, whether you like it or not situation. All physics starts with an observation, and then we take what we observe and we explain things, and those build on each other. So this is kind of our first someone observed this, and it's just how the world works. There's not really much more. Why does it? Great question. Get into that starts to get into philosophy. At some point, physics gets into philosophy. Why do things with mass attract each other? Because there's curved space-time gravitational field. Why does that exist? Because that's how the world works. Again, you get into philosophy, religion, to start to explain why the world works the way it does. At the end of the day, I'm just telling you how the world works. Why you have to philosophy or religion answers those questions. Okay. This force is perpendicular to the direction the charge is moving and perpendicular to the magnetic field. So this is where it gets a little funky. This is where the challenge is going to be. So for example, if I have a positive charge going to the right, and I'm going to teach you all how to figure this out. If I have a positive charge moving to the right, and I have a magnetic field that's going into the page, so we start to use some of our terminology here. That X is into the page. In fact, so B for magnetic field, this is into the page. I'll write it for now, but at some point I'm going to stop writing it. The direction of the force, and unfortunately I put this in the way, B into page. We are going to learn that the direction of the force is upwards. And it's going to totally seem like I just made that up because I haven't taught you how to figure that out yet. Fun fact, you have to use your hand to figure this out, which sounds really stupid. You'll see. We're going to learn how to use your hand to figure this answer out. But notice, The velocity, what does perpendicular mean? 90 degrees. The force is 90 degrees to the direction it's moving. I can't really draw the 90 degrees into the page, but for those that are in the class, this is into the page. This is 90 degrees between this and the force as well. Okay? This is the equation for it. F, what's the value of the force? It's the value of the charge times how fast it's moving, the velocity, times the magnetic field, times the angle. And let's see if I have this nicer later on before I get into it too much. Don't know if I do. I think this is unfortunately just how I put it. This angle is between V. So this is the angle between V and B. This is the angle between V and B. Okay, and we'll talk about that at some point. We can kind of make up some numbers here. If the V and B are lined up with each other, meaning that V and B are in the same direction, let's just kind of make up an example. I have a charge going to the right. So that's its velocity, and a magnetic field that points to the right. I want you all to spend a couple seconds. What is the angle between two arrows that are pointed in the same direction? Spend a few seconds thinking about if the thing is going to the right and B is also pointed to the right, what is the angle between those? The answer is 0. And what does that mean for us? If theta is 0, then the force is 0. Why? I'll write one more step here. Sine of 0 equals 0. Therefore, the force equals 0. So, why does this matter? The direction you're moving affects how strong the force is. If you're moving the same direction as the magnetic field, you get no force. If you're moving exactly perpendicular to it, you do get a force. And something that's really interesting about this, so your phones actually have magnetic fields detectors on them. What's interesting about this is you have your magnetic fields, you have 3 of them. One of them is oriented this way, kind of flat. Another one is 90 degrees to that. Another one is 90 degrees to that, because depending on your orientation of the phone, the force that sensor experiences varies. So you have 3 of them to experience all 3 dimensions. Whatever, you don't need to know that, but fun facts. All right. Okay, how do we figure out the direction of this? And this is where things are going to start to look a little silly. Right-hand rule number 1. The fact that I called it number 1 means that there's more than one right-hand rule. Yay! Okay, right-hand rule number 1. And this is where, if you're online, I will do my best to use my webcam to show this to you, but yeah, it's not ideal. Okay, so there's a bunch of variations on this. There's so many variations of this. I'm just going to teach you one way. If you already know how to do this because you learned it in another past you, use that way. Otherwise, if you found a video online that you're like, look, Dr. James tried to explain it this way, made no sense, I found a video, I like how they did it, use that way. I am just going to teach you all one way, because if I try to teach you several ways, it'll just get more confusing. So, if you find another way that works for you, use that way. So this is I'm just going to do it one way just to make things as simple as possible. All right, so you have your hand flat, so you make a palm, kind of like you're going to give someone a high five. And you have your fingers. Our thumb is not going to be a finger in this case. Our fingers are going to point in the direction that a positive charge moves. Notice how I underlined that. Remember, everything a positive charge does, a negative charge does the opposite. So let's just focus on positive charges. So whatever the direction the positive charge moves, we point it that way. If the charge is going to the right, we point our fingers to the right. If it's going up, we point them up. Down, we point it down, right. Keep your hand flat this entire time. Now, what we're going to do is we are going to rotate our hand, our fingers. In fact, let me put that. And in fact, I'm maybe going to... No. This is fine. Rotate your hand. The wording I had here is good. So that I can curl my fingers So notice how your hand can only curl one way. You can't curl your fingers. I mean, you can kind of curl them backwards, but not really. So we keep our hand flat, and you can only curl them one way. So you kind of move your flat hand around such that I can swing my fingers towards the magnetic field, whichever way that is. If the magnetic field is pointed into the page, I need to swing. We'll do some examples of this. Once you do that, once you have it so you can swing your fingers in that direction, your thumb tells you the direction of the force. Okay? So this is going to make a lot more sense when we actually do some examples. Oh, look at that. A slide with a bunch of examples. All right. Again, I will do this 2 times. I'll do it one in front of the webcam, one in front of the whiteboard. The whiteboard I'm going to do first, though. So this first problem, I have a positive charge moving. We'll say it's out of the page. We'll call that out of the page. So I take my flat hand, I take it, and I have my fingers out of the page. Now, I need to keep them out of the page. If I rotate it like this, I clearly no longer am pointing in the direction it's moving. So I have to do this. I can rotate, look at me go, I can rotate my hand. I need to rotate my hand so that these fingers can swing in the direction of the magnetic field. For example, if I'm like this, if my hand is pointed downwards, I cannot swing my fingers upwards. Like, yeah, okay, kind of, sort of, but not comfortably. So if I keep rotating it while keeping my hand flat, yay, I can swing them upwards in the direction of the magnetic field. The direction your thumb points, that's the force. Okay? I will show this again for the webcam. So yeah, for those online, I have my fingers pointed out. I can swing my hand. Again, this is just not ideal. There's my little webcam on the front of my computer will not do this justice. I highly recommend if this is confusing to you all, you are welcome to try to watch my stream, but there's much better videos where people have much better cameras where you can see their whole body, whatever. Limitation. All right, so I swing this around. I can swing it upwards. So if we do this, we get our force that way. So this is this way, what? That way. These problems take practice, y'all. So this points out, this swings up. There is no getting, like, once you get it down, you'll be good to go. But you have to be able to do this. Like, again, there's no shortcuts to this is the easiest way to do it, this right-hand rule. I would not teach it to you if there was like a easier way. This is what people do. Physicists that have been doing this for forever, we still do this. During the test, you're going to look around and everyone's going to be looking silly doing this right-hand rule nonsense. It will give you like no answers because who knows what problem they're working on. Or if they're doing it right or whatever. All right, so let's try the next one, y'all. Flat hand. You point it in the direction of velocity, which again, this is unfortunate because on my laptop, it's one way. On the screen, it's the other. So, you point it in the direction of velocity. Woo, my fingers point to the right. Again, I can rotate my hand around. If I swing my wrist, I'm breaking that. So I can only rotate. And again, this is maybe another way of doing it. Make your palm point in the direction of B. That's another way of doing it. They're perfectly. So I swing it around so that my palm, oh look, yay, I can point my fingers up in the direction of B. My palm points in the direction of B. What's the direction of my force? Into the page. All right, for those online, again, it's pointed to the left, so I put it to the left. I put my palm in the direction of B, and my thumb points, into the page. So it's kind of tricky there, so I'm actually going to do the X for the force. I do not want you all to think it's like off to the right when you look at this layer. All right, the next one, you should immediately notice a problem. I point my fingers in the direction of velocity. It's straight up. It is impossible for me to point my palm in the direction of that while having my fingers straight up. And we actually talked about this. What's the angle between those two? So theta is 0, and the force is QVB sine of theta. QVB sine of 0 is 0. There's no force. So there's no direction of force if there is no force. All right, see if y'all can figure out the last one. I've got a velocity that's kind of pointed at an angle. It really doesn't matter that it's an angle. You just do the same thing. Point it in the direction of that. Point it kind of out to the right a bit. Make your palm so it's pointing in the direction of B. Your thumb points in the right direction. So if you said the direction of the force is this way, that's correct. Like into the page. Again, it's kind of hard to draw here, but it's kind of into the page. So velocity is this way, palm is up. Let me show you all. So the force is that way. And into the board at an angle. Not very easy to draw on there, but okay. We love it so much. Let's do it again. There is a whole section on the problem set of just do like literally those pictures I drew, those are in the problem set. There's no math required. But can you do the right angle? Can you figure out the direction? Alright, what is the direction of the force experienced by a positive charge in the picture below? This one, I have the velocity going outwards. It's that dot. If you want, you can put a circle around it. So the velocity is out of the page, out of the board, out of the page, whatever you want to call it. And the magnetic field is pointed to the left. So you have, there's just no way to do this in your head, y'all. I've done physics for so long, I would consider my spatial reasoning quite good, and I would not try to do this. Why try to do it in your head? Again, it's like the difference between using a calculator versus doing the math in your head. Why make your brain work really hard? This is really funky. And why does this happen? Because that's just how the world works. This is just what happens, y'all. If you have a magnetic field pointed this way and you have a charge moving, positive charge moving out of the board, it will experience a force. In which direction? Well, we'll find out in 15 seconds. We'll go to 40 seconds. So, you start with your hand pointed out of the page, and then you got to rotate your hand so that your palm matches in the direction of B. At all times, your fingers need to stay pointed in the direction of B. That's the key here. If you rotate your wrist, you're breaking the first rule. So, if you rotate your wrist, for example, so I do this and I say, I want my thing to point in the direction of B. Ugh. Well, now my fingers are pointed upwards. They're no longer pointing in the direction the charge is moving. So, of course, it's not going to give you the right answer. So you point it in the direction that it's pointed, and then you rotate your hand around so that your palm, yes, at some point it's not very comfortable. My palm points in the direction of B. Yay, I can swing my fingers that way. Yay. And your thumb points down. All right, so the answer is down. If you didn't get that, 5, 4, 3, 2, 1. Again, you get to, look at all the online people. They're hearing the answer. That's how it goes. All right. Again, I told you all, the reality is, as much as I would love to do a fantastic job, it is very hard to do both a good job in person and digitally. I learned that when I had to teach high school. When I first taught, my first year of high school that I taught was the year everyone came back. It was half hybrid, half in person, half online. You can't do a good job at both. And there's lots of interesting movies. Anywho, you can only do a good, I can either do really good online or really good in person. I'll prioritize in person because that's the reality of the class. But I try. All right. Same exact problem. What is the direction of the force experienced? Velocity is out of the page. Magnetic field to the left for a negative charge. For a negative charge. And remember, what's the difference between positives and negatives? Whatever the rule is for positive, the rule for negative is exactly opposite that. Everything we've done in this class, anytime we had a positive charge, whatever it did, a negative charge did exactly the opposite. If a positive charge wants to move to the right, a negative charge in that same situation wants to move to the left. Every single time. So we're going to talk about the strategies for what do you do then with a negative charge. So using that knowledge that you know in this class, positives and negatives do opposite things. Using that knowledge, you can kind of figure out what the answer is. I'll go to 115, and then we'll talk about how that interacts with the right-hand rule. In 5, 4, 3, 2, 1. Okay, so in the last problem, if a positive charge wants to go down, a negative charge will go up. It will do the exact opposite. So then how do you figure this out? Well, honestly, use that logic. You use the right-hand rule. If you have a negative charge, you use the right-hand rule like normal. Now, it is very important. Notice, I haven't just calling this the hand rule. The right-hand rule. And we're going to talk about why that is. If you've been using your left hand, even if you're left-handed, it will not work. This is not a whole right-hand people are better situation. This is because the right-hand rule works like the way I'm teaching you all. And, we'll see what happens when you use left hand in just a second. So, you use the right-hand rule like normal. Out of the page. Magnetic field is this way. And when you see it's a negative charge, you say, sure, my thumb is down. I know it's a negative charge. Therefore, the force is opposite that. So when you see this negative charge, you say, all right, find the forces if it was a positive. It's the exact opposite. Now, that's one way of doing it. That's one way of doing it. What you can literally do before coming in on the test, normally I don't want people, writing a bunch of notes in their hand. There's one thing I'll let you do. You can put a big plus sign on your right hand when you come into class. Why? Because on your left hand, if you want, you can put a negative sign. It turns out that if you use your left hand, you get the exact opposite. Let's just prove that to you all. The velocity is out. So I point it out. I put my palm in the direction of the magnetic field, and I get a force that's upward. Your left hand will give you the force on the negative charge. Your right hand will give you the force in a positive charge. Again, you can kind of see this. Boom. Both my fingers are pointed the same way. My palms are pointed the same way. My thumbs are pointed. Left hand is up, right hand is down. So, for those online, there you go. If it's a negative charge, you point it out of the page. Magnetic field's to the right. Boom. But if it was a positive charge, you see. Oh, this is so awkward. There you go. Looks like a fish. All right. I don't know if that was even in frame. All right. So, you just got to practice this, y'all. You'll get a good stretch in on your wrists. It's kind of fun. All right. So let's do some math problems with this. This was just to figure out direction. And you can almost guarantee a problem like this will be on the test. Very straightforward, no math required. Can you find the direction of the force? Because the direction of a force matters a lot. It matters a lot whether or not something is getting pushed up or down. Easy example of that is gravity. If you ever drop something and it started going up into the air, you'd probably say that's weird. The direction of force matters a lot. If you hit the gas on your car, you expect that to push your car forwards, assuming you're in drive. If your car goes backwards, you probably care, because the force is in the wrong direction and you're going to run into something behind you, unless you put it in reverse, in which case you hope that happens. So, the direction of force matters a lot, hence why I need you all to know it. Okay, so, an electron moving at 4 times 10 to the 3 meters per second in a 1.25 Tesla magnetic field experiences a magnetic force of 1.4 times 10 to the minus 16 newtons. What angle does the velocity of the electron make with the magnetic field? And do I want this to be an electron? I'm going to do a proton. I'm going to actually change this problem on the fly. Because remember, electrons are negative, and so it gets a tiny, just a little, we'll do it both ways. But for now, let's just change this to a proton real quick to make it as straightforward as possible, and then I'll make it an electron and say what's the difference. All right? So, what's given? This is a classic, y'all. We got velocity. This is a classic Givens missing equation solve. We have the magnet, and I'll let you all spend 10 seconds. What do you think the givens are? We got some new givens here, so I'll let you all think about it. Because honestly, that's the hardest part of this problem. What's given? What's missing? What equation relates them? There's no right-hand rule here. So the first one is going to be the magnetic, the next one's going to be the magnetic field. B for magnetic field. Again, it's weird, I know, but whatever. I didn't make the rules. Someone in a really old book did. And it stuck. The good news is a lot of the units that we're going to see are ones we've seen before. I've only given you all one new unit. The two of these are ones that you've seen before. Force is newtons. That is always true. Force will always be newtons. And that's something that you hopefully like, okay, I remember that. Newton's laws, all that jazz. If it's a force, it's newtons. And it also said the word force. We are solving for the angle. And conveniently, I've only taught you one equation. So it's that equation. It's the equation that has these things. F equals Q, V, B, sine of theta. All right. So step 4, plug and chug. 1.4 e to the minus 16 equals, make certain you put the things. Oh, we didn't write, like, oh man, I wonder what Q is. And we look back at our problem and say, oh, I don't see it written down anywhere, but then we read it carefully. A proton. So what's the charge? So remember, y'all, this is totally something, this is completely fine to go back to step 1 and add. You don't need to have all your givens the first time. Sometimes when you're solving a problem, so it's 1.6 times 10 to the minus 19 coulombs. That will be given on your formula sheet. I still don't need you to memorize that. Sometimes you go back and realize, I feel like I'm missing something. Is that somewhere in the problem? And you say, oh yeah, there it is. Great. Good job. Like I just did now. I legitimately forgot that I needed to identify Q, and I realized it when solving the problem. Okay, then we have V. I just moved it down because I knew I'm getting tight on room. 1.25. Ugh, still ran out of room. These numbers were all big. Shrink. Times sine of theta. So this is a nice little algebra problem. Remember my recommendation to you all when it comes to algebra. Simplify what you can before you start moving things around. So that right side we can simplify, so I'll do that. 1.6 times 10 to the minus 19 times 4e3 times 1.25. So I have 1.4 e to the minus 16 equals 8 e to the minus 16. Again, I just literally multiplied everything on the right. Didn't do anything fancy. Times sine of theta. You can see anytime there's a blank slide on my PowerPoints, if you ever wonder why I have those, that's because last year I solved the same problem, and last year I also needed extra room. So literally these PowerPoints, on the Friday of this week, I have the PowerPoints with all the writing. What I did last year is I just took the latest PowerPoint I had, and I said, delete all ink, and then put it here. So, anyway. Have you ever why does it keep having all these blank slides in there? That's because I knew I needed it. Because last year I needed it. All right, great. So now you divide. Divide this side by that. Divide both sides. Be very careful and making certain you're plugging things in. So I get 0.000175 equals sine of theta. And this is something my high schoolers depending on where they're at, they may not have seen this. Hopefully you see, what's the opposite of sine? Sine inverse of that whole thing. How do you get rid of a sine? Sine inverse.
Something's wrong.
Yeah, well, you get a very tiny angle, don't you? Yeah. All right, let me see. Yeah, that's a great point, because I was like, I got a really tiny angle. That's weird.
I got 0.175.
Oh, thank you. Let's see what I did weird here. 1.4. Oh, I have no idea why, but great catch. Yeah, at the end, I got an angle of 0.0004. I'm going to go ahead and tell you, I'm not going to give you a problem where the angle is 0.0004. So that's one of those red flag. What did I do wrong? I have no idea why I did this. I plugged in 1.4 times 10 to the minus 19 instead of the minus 16. Great news. Multiple choice tests. I'm not going to put an answer. That's one of the benefits of multiple choice tests. They probably, if you don't get an answer that's within 1 to 2% of mine, you messed up somewhere. I messed up in this case. So I just go back, I fix it. Just to double check, I think you all told me that it was 0.175. Fantastic. And then, yep, that's what I got. Sine inverse of that is 10. There we go. That's a reasonable angle. Make certain your calculator's in degrees mode. I will never ask you for an angle in radians in this class. Okay? So, all right. Cool. Now, something interesting about this. I originally had the problem as an electron. To that end, what does that change about this problem? Absolutely nothing. So, 10.08 is an answer. It turns out there's some symmetry with sine. This answer could have also been 180 minus 10.08. There's technically two answers to this. I'll just remind, so sine of an angle equals sine of 180 minus that angle. That's just a trig identity. To that end, I didn't tell you all specific directions. I didn't say up, down, left, right, whatever, and I'm not going to. I'm not going to make this more complicated than it needs to be. But if we kind of go back, and let me see if I was careful with this. I was not, so let me be careful now. When you do this cross product, something I want to point out here. Let's see. No, the negative matters. How much do I want to say here? You can basically take the absolute value of Q when you plug it in here, okay? If you go ahead and plug in your calculator, let's actually just see what happens. What would change if we had a negative? It would be sine inverse of, let me fix this so people aren't confused later on. It would just be sine inverse of negative 0.075. So if this was an electron, let's jot that down. And we can I can prove this to you all. So that's just a fun fact there. What if Q is negative? What does that change? Theta would be sine inverse of negative 0.175. See what happens when you plug that in your calculator. Okay, technically the angle. Okay, it does make it negative, but that doesn't matter. Whatever. You plug it in, you get negative 10.08 degrees. You may be like, those seem different. At the end of the day, the angle is still 10.08 degrees. What does this look like? The difference, so this problem just said, what is the angle between them? What is a negative angle? It's just a matter of which one's on top, but this problem didn't care. So let me draw you all a picture. Let me show you the difference between a positive 10.08 degrees and a negative 10.808 degrees. So this is my velocity, and this is my magnetic field. This is positive 10.08 degrees. If this is my magnetic field, and this is my velocity, this is negative 10.08 degrees. It's still 10.808 degrees between them. So long story short, I'm not going to try to trick you all on that. The answers will all be positive. A negative angle doesn't really mean much for you, like in the context of this, unless you have a frame of reference. Okay, so long story short, don't stress it. All right. Okay, let's see how much can I talk about. Sure, I told you all. Remember I told you permanent magnets? The next two slides are literally the only two. All right, let me double, triple check before I promise that. Yeah, I think they're literally the only two slides about permanent magnets in this entire thing. So it's what I said at the beginning, but hey, it's in writing. Magnetic field, permanent magnets. Magnetic fields point away from north and towards south. We will need to know that at some point. So when you all are playing with a magnet at home, you know those classic red, blue magnets or who knows what. One end is north, one end is south. Every single permanent magnet has a north and a south. Every single permanent magnet has a north and a south. It is if you discover a magnet that only has a north end or only has a south end, you will win the Nobel Prize. Like, because it's just, as far as we're aware, they don't exist. Every single permanent magnet has a north and a south end. And the first question that people think of when I say that is often, what if I just took a magnet and I split it in half? And that's a great question. What if I just broke it in half? I'd have a north end and a south end. Well, fun fact, if you break a magnet in half, you don't end up with a north end and a south end, or you end up with two magnets. Because and this kind of then gets to the next question. What if I break those in half? I end up with four magnets. And if you just take this all the way, break in half, break in half, break in half, break in half, all the way down to an atom, we actually discover where permanent magnets come from. What's the smallest you can break it down to? Literally an atom. Literally a single electron. Fun fact, a single electron has a magnetic field, top points north and south. A single electron is a permanent magnet with a north and a south end. A single atom with electrons orbiting around it has a north and a south end. So how do you make a permanent magnet? You get all of those to line up. That's all a permanent magnet is a material where all the atoms, all the electrons, at least most of them, are all pointed, their magnetic fields all point the same way. So now you know where permanent magnets come from. Most people are like, it's one of those fun facts. Literally, and a single electron is a permanent magnet. A single atom is a permanent magnet. You get them all to line up, you got a permanent magnet. Like a strong one. The more of them you get to line up, the better. The stronger it is. Okay, and then we got 2 minutes for this last quicker question. This is real weird. Here's a picture. So I just told you all that magnetic field lines point out of the north end and into the south end. So here I have a picture of the Earth, and just to make it more clear, I've got magnetic field lines pointing out of the bottom and into the top. And my question is, where is the north magnetic end of the Earth? Where is the north magnetic end of the Earth? Is it at the top or the bottom? And you're going to use that rule I just taught you. Magnetic field lines point away from the north and they point towards the south. All right, and in case we're running out of time, so I'm just going to literally draw it on here while this is open. The bottom is the north and the top is the south. And then you may be like, but why do compasses point north then? It's because if you put a compass here, if you all have ever played, remember you all the magic rule, opposites attract. The north end of a compass points towards the south end, the south magnetic pole. The north end of a compass points towards the south. When you're playing with magnets, those are the ends that attract. Anyway, I'll spend probably a couple seconds on this next time, but the answer is it's opposite what you expect. And the other really weird thing, at some point, the Earth's magnetic field will flip. And you can look up things about that. Yeah. It'll be an absolute disaster when it happens for reasons. All right. Y'all have a great one. I'll see you Thursday. Yeah, give y'all something interesting to think about. Another existential crisis to have.